Welcome to this explainer. Today, we're literally stepping into the shoes of a geometric detective to unlock the hidden, ironclad rules that govern shapes and the spaces all around us. We're going to build our mathematical toolkit right from the ground up, relying purely on logic, evidence, and structure. Now, I want you to really think about this as we start. What makes a simple, three-sided shape so incredibly powerful? Because as we're about to see, something as basic as a triangle holds these profound laws that literally shape our physical world. I mean, these aren't just arbitrary guidelines, right? They are absolute, unbreakable laws of reality. Okay, let's dive into our roadmap for today. First, we'll meet the isosceles triangle. Then, we'll cover the laws of equality, solve some geometric puzzles, explore the rules of inequality, and finally, look at the shortest path. So starting with part 1, meet the isosceles triangle and mathematical symmetry. Right, so our source defines a triangle with at least two equal sides as an isosceles triangle. But, there's a really fascinating distinction here. If all three sides are equal, well, it's an equilateral triangle. And that means an equilateral triangle inherently satisfies all the properties of an isosceles triangle. But, and this is an absolutely crucial distinction for our toolkit, an isosceles triangle doesn't necessarily satisfy all the properties of an equilateral one. It's kind of helpful to think of isosceles as the broader category of symmetry. Moving on to part 2, the laws of equality, or as I like to call them, the geometric cheat codes. If we compare the two foundational theorems we're working with, it's pretty amazing. Theorem 1 states that if two sides of a triangle are equal, the angles opposite to them are also equal. And Theorem 2, it's the exact reverse. If two angles are equal, the sides opposite them are equal. This right here is the beautiful rule of reciprocity in geometry. These axioms work perfectly in both directions, giving us some incredible leverage to unlock clues hidden within a problem. Now, what's really interesting is how we actually prove this rule of reciprocity. If you picture an isosceles triangle, ABC, where side AB equals side AC, and you just drop a single perpendicular line straight down the middle from the top vertex A to the base BC, well, you instantly create a perfect mirror image. Let's trace the logic on this. We're given that sides AB and AC are equal. When we draw that perpendicular line right down the middle, we create two 90-degree angles at the base. Suddenly, we've got two smaller right-angled triangles that share a center wall and have identical hypotenuses. Because they share these exact specific traits, they're perfectly identical, or, congruent. And because they're congruent, every single corresponding part, including those bottom angles, must match perfectly. All right, part 3, solving geometric puzzles. Let's apply these tools. This brilliantly illustrates how layered geometry actually is. On one hand, we have our basic Theorem 1, but then we have this much more complex puzzle from the source's exercises. It looks totally overwhelming, right? Multiple bisecting lines intersecting at a point O inside the triangle. But if you walk through the solution steps, it's literally just our basic tool applied over and over. First, it uses the fact that equal sides AB and AC mean the large opposite angles are equal. Since those large angles are bisected or cut perfectly in half, the smaller inside angles must also be equal. And that makes the smaller inner triangle, BOC, an isosceles triangle too. It's a complex puzzle solved simply by finding the hidden symmetry within the symmetry. Okay, section 4, the rules of inequality. This is what happens when symmetry breaks. So ask yourself this. What happens to our cheat codes when that perfect symmetry completely breaks? What geometric laws take over when the sides and angles of a triangle are no longer perfectly equal? Well, it turns out chaos doesn't just take over. Instead, a really strict hierarchy emerges. The absolutely crucial point here is outlined in Theorem 3. The rule is simple, but it is absolute. If two sides of a triangle are unequal, the longer side always has the greater angle opposite to it. Even in complete asymmetry, the universe enforces an unbreakable proportional relationship. The wider the angle opens, the longer the side opposite to it has to be to connect the endpoints. It's just a fundamental fact. And guess what? Just like our rules of equality, our rules of inequality have a rule of reciprocity too. Theorem 3 tells us unequal sides dictate the angles. Well, Theorem 4 flips it. Unequal angles dictate the sides. So if you know which angle is the absolute biggest in a triangle, you don't even need a ruler to measure the sides. You automatically know with 100% certainty that the longest side lives directly opposite that largest angle. Moving on to our final section, part 5, the shortest path. Let's see how this logically builds into Theorem 5. This theorem states that of all the lines that can be drawn from a point outside a straight line, the perpendicular line is the absolute shortest. But why? Well, think about the proof. If you draw any other line, let's call it OQ, you create a right angle triangle. Because a right angle is 90 degrees and the whole triangle only has 180 degrees to share, the right angle has to be the largest angle in that triangle. And applying our rule of inequality from a second ago, the side opposite the largest angle must be the longest side. Therefore, the straight perpendicular drop, which we'll call OP, will always be shorter than any angled path. Now, this logic directly gives us the fundamental rules of existence for a triangle, presented as corollaries 1 and 2 in our source material. Rule number 1, the sum of the lengths of any two sides is always greater than the third side. And rule number 2, the difference between any two sides is always less than the third side. Listen, these aren't just helpful suggestions. If you have 3 sticks and they don't follow these 2 rules, it is physically impossible to connect them to form a closed triangle. No way around it. Let's actually apply this to the real world. Imagine you're at point A, say the edge of a park, and you desperately need to get to point C on the exact opposite side. You could walk along the path to point B and then turn and walk to point C. But intuitively, you know cutting straight across the grass from A to C is way faster. Why? Because you are physically tracing a triangle. The triangle inequality theorem dictates that the sum of the detour paths, AB plus BC, must be greater than the straight path, AC. You are just being lazy by cutting across the grass. You are actually obeying an unyielding mathematical law. Now, before we wrap up, I want to challenge you with one final test of your newly equipped toolkit. Consider this higher-order thinking skills puzzle. Question 12 from the text. You have a 4-sided shape, quadrilateral ABCD. You're told AB is the shortest side overall, and DC is the longest side overall. Without a single number provided, you have to prove that angle B is greater than angle D. So what's the genius of the solution? You just draw a single diagonal line connecting B and D. This splits the whole shape into 2 triangles. Then simply apply our inequality rule. Greater side equals greater opposite angle to each triangle separately. Add them up, and the whole puzzle just falls right into place. It's beautiful. So what does this all mean for us? What should you take away from this explainer? Well, whether a shape is perfectly mirrored or totally asymmetrical, it is completely bound by laws of proportion and distance. These simple rules of 3-sided shapes quietly govern the physical world around us, unlocking everything from the foundations of architecture to the incredibly complex physics of navigation across our universe. So, the next time you look at a towering bridge or just map a trip across town, ask yourself, what hidden geometric forces are silently holding your world together?